Welcome to Homework Lib.
So in this question, germanium has an energy band of 0.67 electrovolts. And then we know that doping with arsenic adds donor levels in the gap 0.01 electrovolts below the bottom of the conducting band. So if this does not make much sense to you, don't worry about it because this is not really relevant to the question. So the actual part that is relevant is it says at a temperature of 300 Kelvin, the probability F equals 4.4 times 10 to the negative 4. And this is the probability that the electron state at the bottom of the conducting band is occupied. So we want to find what is the Fermi level relative to the conducting band. So in order to find the Fermi level with respect to the conducting band, what we know is we are looking for E minus EF. This is a relative Fermi energy. And then how do we find that? The probability Fe, according to equation 42.16, is equal to 1 over e to the E minus EF over KT plus 1. And what we're looking for, E equals EF, appears here. And if we look at this, we know it's 300 Kelvin. We know what T is, we know what T is, we know what K is, we know what Fe is. So we really, from this one equation, we can solve for the question, and we don't need to understand what germanium is or what is doping with arsenic. So that is not relevant. The only thing we need to know is the probability that the lower band is occupied, which is 4.4 times 10 to the negative 4. So now we can find what E minus EF is. E minus EF equals, we need a little bit rearrangement of this equation. Turns out it is KT times log of 1 over Fe minus 1. If this is not obvious to you how this happened, we can also do it step by step, because E equals E minus EF over KT equals 1 over Fe minus 1. I'm just rearranging this equation over here. And then from that, we have E minus EF equals over KT equals ln of this. And then that goes to this step. So this is just equation of, again, this is just steps of rearranging the equation. Make sure you don't make mistakes during this process. And then we can finally use all the constants, the actual numbers, 10 to the negative 3 just per T, and then times 300 Kelvin, and then times ln of 1 over 4.4 times 10 to the negative 4 minus 1. This gives us 0.20 electrovolts. Or if you actually calculate in terms of joule, you'll get 3.2 times 10 to the negative 20 joule, but that is 0.2 electrovolts. So this is E minus EF, and the Fermi energy relative to the Fermi energy relative to the conducting band is EF minus E. And this is 0.2 electrovolts. So the Fermi energy EF equals E minus 0.20 electrovolts. What we know is that the Fermi energy is 0.2 electrovolts below the bottom of this conducting band. So this is the energy gap between the Fermi level and the bottom of the conducting band is pretty large compared to kT and T equals 300 Kelvin. And this is because the probability Fe is very small in this case.